So what I'm going to do, I'm going to start off, talk a little bit about SU5 guts in F theory. Some interesting developments in that last year. And that's going to motivate discussion on SO10. And then to finish off, I'll talk a little bit about G-flux and some interesting things that happen with G-flux with SO10. Okay, so for SU5 in F theory, do the usual thing, you combine a Calabi-Yau fourfold, which is an elliptic vibration over a base and has various singularities. In particular, for SU5, we're going to start with a codimension A4 singularity. That gives you your basic gut surface, which has your SU5 gauge group. And for an SU5 gut, we need two types of matter. You need your 10s and your 5s. And these come from SO10 enhancements and SU6 enhancements. These enhancements are in codimension 2. That means they appear as a complex curve on your gut brain, and you call this a matter curve. And you can see that those give you the right representations by simply taking the adjoint of either of those representations and decomposing it down to SU5. And you see you get a number of representations which include the ones that you want. So that's one quick way of seeing it. We're going to do it a little bit differently in a few minutes. And the Yukawa interactions, you need two types of Yukawa terms for your SU5. For the 10 5 bar 5 bar, that comes from a D6 or SO12 enhancement, and your 10 10 5 comes from the E6 enhancement. These are codimension 3 enhancements, so in your compactification space, they appear as just a point in that space. They still fill space-time. Okay, so last year there was this paper by Isao and Yao, and they looked at SU5 guts and they resolved it explicitly. And they found, interestingly, that where we expected to get an E6 enhancement, we didn't quite get E6. We got something that looked like E6, but had a node missing. And this was a potential problem because we wanted the E6 enhancement to get this 10 10 5 Yukawa. But that was short-lived, because next month another paper showed that you can look at it a different way. And if you look at the enhancements as not giving a higher gauge group, but giving new states in SU5, then everything works absolutely fine. So instead of thinking as getting a new group or a new higher dimension to your root lattice, we stay in SU5 and we look at all our states as being just part of that root lattice, and we get the exact weights that give us the matter, and we also get the structure of the 10 10 5 Yukawa. And we also see it has one less component, so we see why you wouldn't see it as being exactly E6 the previous way, but it wasn't the E6 that we needed, it was a 10 10, it was a Yukawa coupling, and we get that exactly. So that works out absolutely fine. So we thought we'll take a look at SO10 and see if we get a similar thing happening there. So SO10, you obviously have your SO10 singularity to start off with. That's your gut brain with your SO10 gauge group. You need two types of matter, you need your 16 and your 10. We get these from an E6 enhancement and a D6 enhancement respectively. And we need a 16-16 Yukawa coupling, which we get from a codimension 3 E7 enhancement. So we start off with the tape form for your elliptic vibration with a D5 singularity. You just look this up in a table, and here the WXY are homogeneous coordinates of the fibre, and our BI's and our Z's are functions on the base, B3. And here we have a singularity x equals y equals z equals 0, and we think that singularity is just being z equals 0 because we only really care about where it is in the base. So we think there's a codimension 1 singularity because within the base it's codimension 1. We then resolve the singularity by performing blow-ups, and we end up with a smooth vibration. And in the process of resolving, the singular locus as z equals 0 splits into 6 components. And if we intersect these components with each other, we get a nice matrix of intersection numbers, and we immediately recognize this as being the negative cartan of SO10, so we have indeed got an SO10 singularity. Then we look at the enhancements. So if you look up in a table, you can see you expect an E6 enhancement, which gives us a 16 at B2 equals 0. But instead of thinking of it as E6, we think of it in terms of the SO10. And here, one of our cartan divisors, these were the 6 components that z equals 0 splits into, becomes reducible, splits into 3 components, one of which is a previous Cartan divisor, and two of which you can look up in a table and see their weight vectors of a 16 representation within SO10. So where you'd expect to get an E6 enhancement, we say we stick in SO10, but we get the 16 as required, and that's the important part. We don't really care that it's E6, we care that we've got the matter that we wanted. And similarly for the 10, where you'd expect to get an SO12 enhancement, one of your Cartan divisors splits, and you end up with some states which you can look up in a table and you see, right, they're in the weight vector for 10, so that's happened absolutely fine. And so I should say a little bit about the notation here. I probably should have said that before I started going on about it. The vectors are the intersection numbers with all the Cartan divisors, and what I've done is 6 Cartan divisors. One of them corresponds to the extended route, and I ignore that one, so I think what's happened is 5 Cartan divisors, and so all my vectors are 5 vectors, and it's just a set of how many times it intersects each Cartan divisor. Okay, then we come to the Yukawa, and that's going to be where the matter curves meet, so you could have guessed it's going to be where both B2 and B3 are 0. And you think, right, we're going to start from B2 equals 0, where the 16 was located, and if we then set B3 equals 0, one of the states, it's 1, 0, minus 1, which you can see at the top right there, splits further into 2 components. One of these in the 16, and one of them's in the 10, so you think of that point as being where you've got a 16, a 16, and a 10 all meeting, all homologous to each other, and so you've got your structure of your Yukawa interaction. Now, how does this relate to what you had in the SU5? Well, let's go back a little bit. If you look at where we had the 16, one of your Cartan divisor splits, you get another Cartan divisor and 2 new states. So altogether you've got 1 extra component, and E6 has an extra component in SO10, so that's what we expect. However, where your 1, 0, minus 1, 0, 1 split, if you look at what it's split into, they're both, one of them is something you've already got, and the other one is something new. So you've not actually got an extra component there. So you've got E7, but only with 7 components instead of the 8 components you'd expect extended E7 to have. So it's exactly like what we had with SU5, in that if you made a dinking diagram of it, you'd have 1 node missing, and it might look wrong if you did it in another formulas. Okay, so let's talk a little about G-flux. So after doing the Yukawa coupling nicely, we thought we'd have a look at G-flux, and in particular, G-flux has to satisfy a number of conditions. One of them is this quantization condition, and this is the one that caused us a few problems. So we took our G-flux, we solved for all the other conditions it must satisfy, orthogonal to horizontal and vertical divisors, and also it can't intersect any of the Cartan divisors, otherwise it would break your gauge group. And that's fine, but then when you try and impose your quantization condition, you find that you can't. And we thought for a long time we must have made a mistake somewhere, because we kept trying, and we thought this quantization condition obviously has to hold, and we're only able to satisfy it if we put additional constraints on either the base or the gut surface S2. And we actually went back and started again twice in the process of doing this, because we were so certain it must be us that's made a mistake. But then last month, this paper showed that we would expect to get a G-flux that you can't quantize nicely without any additional constraints. And they showed it by looking at the local flux for a number of different gauge groups in a general case, and they showed for certain gauge groups, including SO10, it doesn't quantize nicely automatically. And so we went and we made a list of the possible constraints that we can impose to make that quantize nicely. And what we found is that if you look at the local flux, that's the easiest way of seeing what conditions you have to impose. And impose the conditions, you can solve the global flux straight away. It matches perfect, and the result matches perfectly with the local flux as well. And also the result of your G-flux, of your global G-flux, also matches previous work done on SO10, same chirality induced. Okay, so to sum up, we looked at SO10 and we saw it's similar to SU5 in that you would have a node missing in your singularity at the Yukawa enhancement. So just like the SU5 had 1 missing from E6, we've got 1 missing from E7. But we also saw unexpectedly that the G-flux quantization condition requires you to plug in some extra constraints, and that leaves some obvious open questions. Firstly, there's a number of constraints that are possible, and it's not obvious whether any of these would be preferred, or any way of maybe choosing one over the other. And another question is maybe see if instead of having to just impose these constraints by hand, there could possibly be a way of showing that these constraints automatically are imposed. Again, that's something, possibilities for further research. Okay, so that's all I've got to say. Thanks for listening.
When ESO performed this blow-up, they found the fact that one node was missing and also the multiplicities were wrong in the linking diagram. So my question would be, of course, then Sheffer-Nameki and Thomas Sarno showed that, as you said, that the weights are the things that count. Do you know what the wrong multiplicities correspond to in terms of the weights, and are they also wrong for SO10?
We didn't actually look at that because, well, for me, when I looked at the ESOIR paper, the thing that, yes, the multiplicities were wrong, but the thing that stood out the most was the fact that the E6, and that seemed to be the biggest problem, so we looked just at that. You can see the multiplicities, though, by looking, so for example, when we have some of the breakings, if you get something you've already got, then you could correspond that to a multiplicity too, and you could work them out. But we didn't bother because we showed that the structure was such that it worked anyway. It's the fact that you get the Eukarya interaction in the matter that's important, not that the singularity has the exact form of whatever you want. So we didn't actually look at that, but so I can't answer that. But it's not, again, it's not important that the Eukarya coupling comes out perfectly anyway.
Another question?
This additional constraints on the fluxes, what were these again?
So not on the flux, they're on the surfaces. We got three constraints. We could either make the first Chern class of the base an even class, and the same thing for the gut divisor S2. And another one we had was making the homology class of the base of the gut divisor itself a multiple of 4. That worked as well. So, and they're the three that we've got, and they allow you to quantize it nicely.
And is it actually what that means? I mean, you have this Y4, but do you have an explicit form for Y4? Do you have a global model for that?
So, well, the Y4, we don't specify the base. We just say our functions are on the base. We don't say anything about that, but we see that with the G-flux, as far as we know, you have to then put in some extra constraints on the G-flux, on the base, sorry, in order to get a consistent G-flux. But yeah, we don't say anything about the base until then.
Isn't it enough that the gauge divisor is no spinner to use unquantized gauge flux, unquantized G-flux in the
So say that again.
So at least for unitary groups, we saw that when the gap divisor is not spinner, then G4 is half quantized. Is the situation similar for SO10?
When the gauge group is?
When the gauge stuck the divisor is a non-spin manifold, then automatically
what would non-spin correspond to? I don't.
C1 odd.
This is even odd then, and he said that it has to be even. Or what was it?
Yeah, it has to be even C1 of B3 or C1 of S2. They have to be even.
Yeah, for SU5 it works. For SU5 or S6, it's automatically satisfied. For SO10,
That's my question. Not automatic.
Oh, okay, yeah. Yeah, so Sakura was giving a talk on Thursday, which I think looks at this in more detail. But yeah, certain gauge groups it automatically works, and certain ones it's not. It wouldn't. SO10 it wouldn't. SU5 and E6, for example, it does work nicely.
All right, let's move on to the next speaker. So.